listed as organizer, I didn't do anything. So I would like to thank the other organizers for doing everything. So it's a pleasure to be here. So I would like to talk about some recent works about dispersal in heterogeneous environments from the evolution point of view. Okay, so I'm going to focus on 4 topics. The first topic is called to move, or to stay or to move. Okay, I'll give you 2 examples. Okay, so sometimes it's better not to move, and sometimes it's better to move as fast as you can. Okay, depends on the models and depends on the biological processes behind. And then I will try to introduce a theory called ideal free distribution. Okay, this is a habitat choice theory. Okay, try to use this theory to explain the predictions of the previous 2 models. Okay, once I introduce the ideal free distribution, then I can talk about more examples of dispersals called balanced dispersal. Okay. Of course, once you talk about balanced dispersal, one has to talk about something non-balanced. Okay. If you haven't seen this terminology before, so don't be scared, because it will become very clear later on. Okay. Okay. And of course, different people have different understandings of some of the terminologies. Okay. Okay. All right. So the question I'm interested in is if you use if some organisms sit in some inhomogeneous environment, okay, how should those organisms do? You know, how should it move? How should it distribute itself to somehow maximize the probability of reproduction, for example? Okay, if the environment is completely homogeneous, probably you don't care, right? You just move wherever you want. Okay, in random dispersal, for example. And so the question is, what do you mean by optimal, right? Okay. In control theory, you can have a payoff plus minus the cost. That'll be your thing to do, right? For in controls. But we are going to use a fairly well-known thing in evolution game theory. Okay, it's called evolution stable strategy. Okay, this concept actually was introduced by John Mayer Smith and Nick Price in 1973. Okay, they borrowed the idea from the classical game theory from economics. Okay, the so-called Nash equilibrium and so on and so forth. Okay, so the John Mayer Smith and Price idea is the following. So there are 2 phenotypes. So you can think about one population, but 2 phenotypes. One phenotype is, you can call it resident. Okay, the other one is called a mutant. Okay, so sorry, it's a mutant. Okay, so okay, yeah, that's good. Thanks. Yeah. So what happens is the following. So we call a strategy. So is evolution stable if all the resident, the members of population, say all the resident adopts it. Okay, and assumes the resident is already at equilibrium. Okay, reaches equilibrium. Then you try to introduce a mutant, maybe with a different strategy. Okay, then the mutant with other strategies cannot invade it. Okay. So this is a, descriptive words. Okay. So how to define it precisely in terms of mathematical terminologies? We will see that later on. Okay. We can define use the so-called invasion exponent, which is really eigenvalues. Okay. Okay. It turns out evolution stable strategies does have a close connection with a Nash equilibriums. Okay. In some sense, evolution stable strategy is a strict Nash equilibrium. Okay, we'll also see that a bit later. Okay. Okay. Any questions? Okay. So all my talk is about try to, as in my title, try to find evolution stable strategies. Okay, so I'll show you a couple of examples. Okay. Before I move to the, so I'm going to focus completely on PDE models. Okay, but before I talk about it, there are patch models. For example, Simon Levine in his work in '76 is about 2 patch models. You can ask the same questions for patch models, which is discrete space continuous time models, or discrete space of difference models, or non-local models. Okay, you can ask all the same questions. Okay, and there's a lot of work on this topic called evolution of dispersal. Okay. All right. So now let me go to the first model. Okay. So before I talk about the evolution, so I first have to talk about the resident. Okay, which is one population. So let me just take a so-called logistic model. This is actually after some scaling, already have some scaling, okay, because, for example, the carrying capacity is rescaled, for example, okay. So this model, so it's quite well known, okay. So U is the density of population. M of X, so this is D is a dispersal rate, okay. This means it's a random dispersal, okay. And the population has a growth term, M of X, which depends only on X, okay. If it depends on both X and time, we don't know how to do it, okay. So in some sense, you can think as M of X as the growth rate minus the death rate. For example, the death rate can come from harvesting, okay. Of course, this form looks a bit special, okay, but mostly for simplicity of presenting results, okay. You can go to more general forms, okay. Could be replaced by f of xu, for example, under certain conditions on f, okay. So and I'm going to consider everything in a bounded domain, okay. So, and assume it's a no flux bounded condition, so that the system is closed, which means that the dispersal will not lose any individuals. Okay, so total population will not change if the organism disperses only, no reaction terms. Okay, so it's a closed system. Okay. The point here is that so I put the word strategy here. Okay, because I'm going to find evolution stable strategies. Okay, so I have to specify. I have to tell you what the strategies I mean. Okay, so here the dispersal rate is a strategy. Okay. For example, if you go to talk to experimental people who study butterflies, okay, there are many types of butterflies, some with larger wings, some with small wings, okay, and different size of wings certainly can correspond to different dispersal rate, okay. In fact, butterflies with larger wings can fly much further, okay, which is part of the reason why they expand the range of the butterflies, actually. Okay, the smaller ones, so the butterflies with small wings usually stay near around the center. Okay. All right. So this is so the question is the following. The question is there a dispersal rate D which is evolution stable, which means if you adopt it, no other rate can invade you, okay, can replace you, okay. This means that you have to go to 2 species model, okay. So this is a model introduced by Dockley and his collaborators in 1989, okay. I was one of the reviews for the article, actually. So that's how I got interested in this. So here, now you have you can think about as 2 phenotypes of one single population, okay? The species U, you can think as a resident, okay? And the species V as a mutant, okay? And you can see the mutation only happens at the dispersal rate, okay? So in other words, when we talk about mutations, we always try to restrict to some class, okay? And the two species, they compete completely neutral, okay? So in other words, the coefficients all the same, which is really as a neutral competition here, okay? So in other words, you don't see any difference of the two phenotypes in their competitive ability, okay? Except how fast they move, okay? When I first saw this, I saw it looks a trivial model, you know. How can anything interesting, you know, can come out of this kind of model, okay? Well, it turns out that there's a bit something interesting. So I'm going to assume, for all my talks, I'm going to assume the function m, say it's positive, C2, okay, but not a constant. It's not a constant to mean the environment is inhomogeneous, heterogeneous, which is, okay, my main focus, okay. So the result they give is the following, okay. Well, maybe, so mathematicians will ask, okay, what happens if the two dispersal rates are different, right? If the same, then you don't see any difference between the two species, right? What happens if they're different? What is the dynamic of this model if you have two different dispersal rates? Do they coexist? Or do one of the species will outcompete the other? So-called competitive exclusion will happen. Or does the outcome depend on initial data? Okay. It turns out the answer is very simple, but it's interesting. So the result, this is I'm actually stating a special case of the result. Says the following: suppose the function is continuous, well, positive and non-constant. Okay, if d2 is less than d1, that means the mutant is moved slower. Then you can prove the mutant will outcompete the resident. So 0v star is global stable for any non-negative, non-trivial initial data, okay? So here, v star is a unique positive solution of the single equation. And this single equation is exactly when the species u is not there, okay? So if we think about this again, it's a bit interesting because this tells us that you should move as slow as possible. And also implies in this case that there's no ESS in this case. Well, maybe 0 is ESS, okay? Because if you give me any positive dispersal rate, I can always use a smaller dispersal rate to invade you and actually drive you to extinction. Okay? So how do we visualize this, okay? So if you think about this, so for example, the horizontal axis is d1, vertical is d2, okay? And this middle line is exactly where d1 is equal to d2. So here, in the beginning, when we start, we only see one phenotype, okay? Because d1 is equal to d2, you only have one phenotype, okay? Now, what happens is so mutation can go any direction, right? Okay. So in this case, the mutation is such that the mutant has larger dispersal rate. Because d2, at this position, d2 is bigger than d1, right? Okay. So according to the previous theorem, then the resident should drive out the mutant. The mutant should disappear. So this means that the competition, so this competition is what the model is about. Okay? So the model is only concerns competition part. Okay? So the competition will take you back to original case. So in other words, you don't see higher dispersal rate because it will go extinct. Okay. Of course, what happens if the mutation is becomes slower? So in this case, the mutant has a smaller dispersal rate. Okay. And then the competition will take you to a different spot, okay? Because the slower dispersal will win. Once the wind wins, it becomes a new resident, right? And if this process goes on and on and on and on, you'll see, what you observe is that the dispersal rate of the population becomes smaller and smaller and smaller, okay? So of course here I'm assuming different time scales, okay? Because mutation is a bit rare, okay? And competition is fast, okay? So this is a case, so-called evolution of slow dispersal, okay? In some sense, in this case, it shows that no positive dispersal rate is ESS. You cannot find ESS in this case, okay? So that's the first example, okay? Now let me go to another example, okay? I'm from Ohio, okay? So this is, there's 2 lakes in those regions, okay? This is a Lake Erie, okay? North of Ohio, okay? And this is Lake Ontario, okay? And the rivers, actually this river is going north, okay? It's a bit unusual, okay? Going north, okay? Called Niagara River, okay? In river systems, same questions you can ask, you know, how will the dispersal of organisms evolve in rivers, okay? It's slightly different in rivers because there's water speed there in rivers, okay? So one of the probably the simplest model is the following, okay? It's probably as simple as one can go, okay? So again here, U and V, there are 2 populations, okay? Again, so now this is a 1 dimension because you can think as river as just an interval from 0 to L, okay? Of course, river is really 3-dimensional. You can also model it, no problem, okay? The new feature of this model is that the organism, they have a flux here, okay? Because there's a water speed here, okay? So this alpha is positive. You can think as a river water speed, okay? I'm cheating a little bit. It's not exactly as a river speed, okay? But you can intuitively think that way, okay? Now, the competition again is neutral, okay? Actually, it's even simpler. The growth rate I just normalized to be 1 actually, okay? 1, okay? However, for river models, one interesting thing is the boundary conditions, okay? At x equals 0, we usually call upstream, okay? Upstream of that. I put the no flux boundary condition there, okay? For this model, what is pretty interesting is the boundary condition at the bottom, so-called the downstream, okay? At the downstream, what we put is that we put a ux equals vx equals 0. This condition is not 0 flux, it's not, okay? So what does this condition mean biologically? So roughly speaking, it means that there's a partial loss of individuals into the lake, don't come back, okay? So in other words, there are a proportion of individuals which is washed down to the lake, do not come back, okay?
The last condition is called at x equals 0.
Is this one?
Yeah, x equals 0, and the up one holds at x equals L.
No. On the upstream,
yeah.
For example, there's a dam there, okay? You know, so the fishes cannot, when the leeches come back, reflect back, okay? So there's no flux upstream. Of course, you can put different boundary conditions. But on the downstream, I'm assuming, for example, it's a lake, okay? The lake, so in this here, there's no alpha anymore because part of the individuals are washed to the lake by the water flux, okay? Okay, so in this case, the question is, because the two populations, the only difference is D1, D2, okay? Okay. Maybe I should write it more, okay? So on the bottom, it's really dux minus alpha u is equal to minus alpha u at x equals L, right? So this is a flux, right? This is flux. And this tells me there's a loss of the at the bottom. Maybe this is better, right? Okay. 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 So the question is again, is any dispersal rate which is evolution stable? Okay. Is any something optimal there? Okay. And the answer is no. Okay. So this is a recent work with Fischer-Lucha. So what we prove is following. It's something opposite happens. Okay. If D1 is bigger than D2, so this means the resident has higher dispersal rate. Okay. Then U star 0, when F exists, is global stable. So in this case, so the U star is a positive solution of the single equation. Okay. So in other words, in this case, it's better to move faster. Okay. Biologically, it's not too difficult to understand because otherwise, if you don't diffuse too faster, there's a possibility you'll be washed down to the lake and don't come back. Okay, so you want to diffuse faster, have a more probability moving upstream. Okay. This solution may not exist. Okay, because for example, when alpha is very large or when D1 is very small, this problem may not have a positive solution at all, because all the populations are washed to the lake, don't come back. For example, when D1 is sufficiently small. Okay. Okay. So in this case, it's disappointing that again there's no ESS in this case. Or you can say infinity is the ESS. Okay. You want to move as fast as possible. Okay. So I give two examples. Yes.
If mx is not always positive, do you have any result?
For the first model or for the second model?
For the first and second.
Both. So for the first model, it doesn't really matter. The same results holds when m changes sign. For the second model, when m is not constant anymore, it becomes rather complicated. Surprisingly complicated. Yeah. So I'm still working with Fischer-Lucha and one of my postdocs, Adrian Lan. Okay. In that case. Okay. Okay. The reason is because this kind of dispersal has a certain direction. Okay. Then, when this 1 is replaced by m of x, monotone decreasing, monotone increasing, biologically they are different. Okay. It's a subtle then. Okay. But for the first model, it doesn't matter. When m changes sign, no problem. Okay. Yeah. That also has something to do with the monotonicity of the dominant eigenvalue with respect to these parameters, whether they are monotone or not. Okay. Yeah. So there's a conjecture in this case, so we don't know how to prove it. Okay. If you replace the boundary condition at the downstream by U of L equals V of L equals 0. So in this case, we have a numerical simulation which seems to suggest there is some optimal dispersal rate. Not too fast, not too small, but we don't know how to prove it. This case is particularly interesting because if you think about the freshwater fishes, okay, and the downstream is the ocean, okay, then the freshwater fish cannot survive in the ocean. Okay, so the density near the ocean for them is very small. Okay, or a waterfall, for example. Okay, So what I'm trying to say is that the predictions of the models, of course, depend on the boundary conditions for this model. Okay. Okay. All right. Okay. So how to prove these results? First of all, let me tell you mathematically how to prove these results. Okay. Then I'll talk about some biological interpretations. Okay. I'm going a little bit slow. Okay. All right, so this can be done by the monotone dynamical systems, for example, which is essentially comparison principle for these two species competition models. Okay, there's a lot of work on monotone dynamical system theory. Okay, for example, for this model, if M is positive, usually you have two semi-trivial steady state. Okay, to prove one of the semi-trivial states is global stable, then what you need to prove is two things. Okay, first of all, you prove there's no coexistence steady state. Okay, and then then the local stable steady state is global stable. Okay, okay. So the mathematics really boils down to two things. First of all, you prove there's no positive steady state. Okay. Second thing is to prove, determine which one is local stable. Then you know everything. Okay, and the proof for the previous results are all follow from this line. Okay, except the details are very different because the models are different. Okay, the conclusions are different. Okay, but this is the general idea. So that's the mathematical methods behind. Okay. Of course, usually the subtle part is to prove this part. Okay. What about biological reasons? Okay. So this, I move to the second part. This has something to do called ideal fluid distribution. Okay. So this is a theory proposed by Fredwell and Lucas in 1970. Okay. The question is the question is the same as I proposed earlier. How should organisms distribute themselves in homogeneous environment? Because the distribution you observe is usually stable in some way. Otherwise, you will not see it. Okay. They should resist mutations, okay, of other strategies. Okay. So this theory has two assumptions. Okay. The first assumption is that the organisms are ideal. What this means is that the organisms, they know everything about habitat, its habitat quality, and its enemies. Okay. So on and so forth. Okay. The other assumption is that the organisms can move without any cost. Okay, and the prediction is that organisms should aggregate proportion to the amount of resources. Well, this is easy to understand if you think about it. Okay, if there's more food, okay, somewhere, of course you can see more individuals there usually. Okay. But the key word is the word proportion. Okay. So what does that mean? Biologists, of course, they want to test the model experimentally. Okay, and there are many experiments. The first experiment is done by Philip Milnitsky in '79. Okay, so what he did is that he just got a water tank. These are like chemostat models. Okay, but slightly different from the usual chemostat, because there's two pumps. Okay, and the left pump for example, you see 5 water frees here. This means that, for example, for every 10 seconds, you pump in 5 water frees, and this means for every 10 seconds you just pump in 1. Okay, so in other words, the influx rate is different. Okay, and the fishes also aggregate 5 versus 1. Okay, so now you see the word proportion. So in other words, the total number of the resource divided by the total number of the fishes here should be the same ratio in different locations. Okay. You might think this is completely unrealistic. Okay. But sometimes it is actually. Okay. I was in Shanghai this April to June for And I lived in suburb, okay, but also travel quite a bit into the downtown, okay. In downtown train station, you can see a lot of taxis are waiting, okay. But if you go suburb, further away, you see fewer and fewer taxis waiting outside the subway station, okay. Maybe something similar for Korea and Japan, okay. Well, these taxi drivers, they are like okay, so we are fishes, right? We are fishes, okay. We are the resource, okay. However, you see the ratios, okay. So if the taxi drivers really know everything, maybe the ideal free distribution is what they should do as a group, maybe. Okay. I don't know, okay. Another example is that when I entered Korea yesterday, okay, the passport control, okay, and you can see the line is almost equally long, right? The waiting line. Because people think the food is the same everywhere. Each officer maybe handle the passport same time, but actually it's not exact same time, okay? But so in that case, it's like environment is homogeneous, right? Then the populations will also distribute homogeneously without thinking too much. Okay. All right, so why this has anything to do with our PDE model, right? Well, this is some connections. So let's look at the first model, logistic model, okay? So this model is a logistic model. So for any positive initial data, the solution will converge to a unique positive steady state, okay? And if you think about it, what is ideal free distribution? Well, it simply means, so the question is, does this solution reach ideal free? Well, in something means the resource divided by the density, is that a constant function, right? Is that ratio as constant everywhere, okay? If it is, then it is ideal free, otherwise it's not. But for PDE people, we know this is impossible, right? And it's very easy to prove this is impossible, okay? And you can easily prove by maximum principle, for example, that for any dispersal rate positive, okay, this ratio is never constant, okay? Actually, in locations M has maximum, then this ratio is bigger than 1. When at locations when M reaches the minimum, this ratio is, sorry, I reversed. No, I'm right. When M reaches a minimum, so let me draw a picture maybe, okay. So this is M of X, okay. So a typical U star will be, say, something like this, okay. So the ratio is never constant, okay. However, if you take a limit, okay, if you let the dispersal rate go to 0, you can see the ratio, of course, is constant, okay. So what this means is that if you let the organism move slower and slower, it's matching, it's becoming closer and closer to the ideal free distribution. It consumes, the organism will consume almost all the resource, right? So which means it doesn't leave anything for your competitor. Of course, your competitor cannot survive, okay? That's the idea, okay? So that's the first model, okay? Second model is same thing, okay? You can exactly do similar thing. And for example, you can prove that for any dispersal rate, now the resource is constant. Over U star of X, you can show this is never constant, which means U star is never constant, okay? But on the other hand, you can also prove when you let diffusion go to infinity this time, not go to 0, U star actually converge to a constant, okay? Interestingly, the water speed, alpha comes in, the length of the river also comes in, okay, in this case. Okay. All right, so this is the second part, okay. So goes to my third part, okay. How can we use these kind of ideas to really propose some models which can produce ideal fluid distributions, okay? Because the previous two examples, they don't, okay? Well, there are many ways to do it, it turns out, okay? And this is what I did with Steve, he's here, and also Chris Kostner, okay? So what we did is that we just put one advection term, okay? We are naive, okay? But just put the advection, so this advection along the gradient of some function, p of x, okay? So in other words, the organisms, they are not just doing the random dispersal, but also try to move in certain directions, okay? It turns out there's one p of x which is very special, is log m of x, okay? The dispersal rate times log m of x produce ideal fluid distribution in this case. Why? So let's look at this more carefully. So we look at the steady state problem. D gradient u minus du gradient of log m, okay? And you can easily check u equals m is a positive solution to this problem. Well, this is 0, right? And also that the flux is also 0 because it's d gradient of m minus m gradient of d log m, and that's 0, okay? This is quite a bit special, something called balanced dispersal, okay? So balanced dispersal in some sense means that the organisms, they move, okay? However, the flux, the net flux is 0 everywhere, okay? And this was, biologists actually, they use patch models to start this really early, in 1992, for example, okay? Of course, the question is that, is such a strategy ESS, okay? Because I want to find out ESS, okay? So what do we mean? So again, we go to two populations, two species, they compete, okay? So here, the two species, they compete for the same resource. They also have a random dispersal. Now, they also move along some gradient of p of x and q of x, okay? With no flux boundary conditions, okay? And as I said earlier, if p is equal to dispersal rate d1 times log m, then m0 is always a steady state, okay? So what do we mean by evolution stable? It simply means the following, okay? So the question is this steady state locally asymptotically stable? In other words, is this strategy ESS? Because if it is locally asymptotically stable, it simply means that when the mutant V has a small initial density, then as time goes to infinity, V of xt will go to 0. That's what it means local asymptotic stability, right? The mutant will disappear, okay? It turns out if you try to linearize it, okay, it doesn't work because you can prove 0 is always a dominating value, okay? So for ideal fluid distribution models, you almost always have the same problem, okay? The Lyapunov linearized method just doesn't work, okay? So what you can do is that, so this is built on two works, okay? The theory is the following, okay? Suppose the function C2 non-constant and positive, okay? If p is equal to d1 log m, q minus d2 is non-constant because there's a gradient before q. So let me go back. Because there's a gradient before q, if you add any constant, it doesn't change anything, okay? So this simply means q is not d2 log m, okay? Then you can prove this steady state is global stable actually, okay? So this means this strategy is ESS. Okay. Of course, here, when we talk about something is evolution stable, you have to think about which class we are talking about here. So the evolution stable here means the strategy here means the functions P and Q now. Okay. I'm fixing everything else. Okay. So the strategy can resist the invasion of other strategies. Okay. This is ESS. It's more than that. It can replace any other strategy. Okay. Okay. So this is one example of evolution stable strategies. Okay. Okay, I'll skip the proof because I'm running out of time. About 10 minutes or so, maybe. Okay, I think you need to rush it a bit. Okay, so you can find many other examples. Okay, for example, Mark Lewis suggests it's Laplacian of U of M. Okay, if you are familiar with the cross diffusion model, for example, this is a typical cross diffusion rate here. Okay, and also a former student of Professor Cantrell, Dan Ryan, he derived a really interesting case. Okay. All right. So in other words, there's some interesting modelings here. Okay. And Yongzhen you will talk about another type of ideal field diffusions. So we'll see how we compete with different ideal field diffusion strategies. Okay. Yeah. There are many others. Okay. Yeah. Okay. For example, fitness-dependent dispersals. Okay. That we touched. Okay. So now let me last time I'll talk about this non-balanced dispersal. Okay. This case is mathematically tough. Okay. The reason is because we'll see that the reason a bit later on. Okay. Okay. This line of research was a project initiated by Chris Kostner. The first paper was by Chris Kostner, his former student, in 1995. Okay, that was his thesis, I believe. So what they did is that they introduced not a log m anymore, just minus alpha u gradient of m. Okay, so the organism just try to track the gradient of a resource. Okay, okay. Then you can ask many questions if you go to two species. Okay, so for example, this is what Steve Cantrell, Chris Kostner, and I can see in 2006. Okay, you can think about the following. Let's think about V now as a resident, which is just doing the random dispersal. Okay, suppose there's a mutation. Now the mutation could be on D1, but also could be on this part. So in other words, maybe the mutant is smart. Okay, maybe the mutant can also try to move along the gradient of the resource. Then the question is, what happens? Will mutant survive, or will the mutant drive the resident? Okay. It turns out that when alpha is positive small, the mutant does have advantage. Okay. And our first result says the following. Okay. Our first result says that if m is C2 positive and non-constant, if D1 is equal to D2, alpha is positive, small, and omega is convex, then U star 0 is global stable. So for this case, the two organisms are same, except the mutant has a small advection along the gradient of the m. So this means having a small positive alpha give you an advantage. So the selection will. So if you think about this, if you after a long time, what you'll see is that the population not just doing the random movement, but also try to move along the gradient of the resource a little bit. That's what you'll observe. Okay. So small advection is good, is a favorite. Okay. What happens to large advection, okay, when alpha is very large. Because mutation is rare, but the mutation can be large, okay. It turns out something surprising, really surprising happened. You might think when alpha becomes very, very large, it should be good it should be beneficial for the mutant, but it's not necessary so. You can prove such a result. For any D1, D2, if alpha is bigger than D1 over the minimum of M, then both semi-trivial steady states are unstable, and the system has a stable positive steady state. The two species actually coexist. So this means that the large advection may not be advantageous. So what happened? Okay. It took us a while to find out what happened. Okay. And intuitively speaking, maybe some intermediate advection is evolution stable. So maybe there's some alpha hat. So this alpha is equal maybe something, okay, some fitness, okay. Maybe there's some alpha hat which is optimal, okay. Well, what does this curve mean? Well, it means some selection gradient or something, okay. Okay. So this is what okay, maybe I should skip this part. Okay. So for the coexistence, there's quite a few interesting works. Okay, let me just skip this part maybe. Okay. Okay. So now let me go through again because I'm interested in evolution stable strategies. Okay. The question is there any advection rate which is evolution stable? Okay. So what we did is that again we considered for simplicity, let's just assume the two species have the same dispersal rate. And I rescaled that the alpha beta are rescaled. Okay. Okay. And again they have the same competition for the same resources. Okay. Well, there's a conjecture. Let me conjecture is the following. Under suitable assumptions on M and omega, okay, there exists some alpha hat positive, such that if beta is less than alpha, is less or equal to alpha hat. So the beta is here, alpha is here, okay? Or beta is here. To be safe, okay. So this conjecture says that you can see for both cases, this is beta is less than alpha, less than alpha hat. The other case is that beta is larger than alpha, alpha is larger than that, right? So what this means is that alpha is closer to alpha hat. So this simply means that if alpha is closer to this alpha hat, then your star zero is global stable. The question is, does such alpha hat exist or not? You don't know, right? Because the model doesn't say anything. Okay? Now, the next thing says that if beta and alpha are the two different sites, then they coexist. Okay? And as you can see, this is exactly an extension of the previous two results in some way. Okay? So the question is, how can we determine such alpha hat? Okay. Okay. So what is this alpha hat? Okay. So now a typical approach is adaptive dynamics. Someone here is going to talk about adaptive dynamics in ecology. Who is that? Okay. Okay. So maybe my talk should be behind after your talk. So the adaptive dynamic approach is like this. Okay. Suppose the species U is at equilibrium. Okay. And then you ask, can species the mutant V grow when it's rare? Okay. So what you do is the following. You try to study the stability of the U star zero. Okay. Well, when you study the stability of the semi-trivial steady state, you are reduced to solving a linear eigenvalue problem, just one. Okay. And this linear eigenvalue problem is the divergence of gradient phi minus beta phi gradient m plus m minus u star phi is equal to lambda phi. And let capital lambda denote the largest eigenvalue of this problem. Okay? Now, the capital lambda depends on both alpha and beta. Why? Because, well, beta is here, right? And also the eigenvalue depends on U star. U star depends on alpha nonlinearly, of course. Okay. So why this has anything to do with evolution stable strategy? Well, now I can give the precise definition of the here. So what is alpha hat is evolution stable? Well, it means the following. Maybe I also need to draw a graph. So this is alpha is equal to beta, okay, line, okay? And you can see, easily see the lambda is always 0 on the line here, okay? Now, what you do is the following. What you do is that, can you find a curve here? This is alpha hat. On this curve, lambda is also equal to 0, okay? So it's a singular point, okay? So what this means is that, can we find such alpha hat such that this function at alpha hat beta is always less than, this is equal to 0, right? So in other words, can we prove this is negative essentially, and this is positive. Can we do that? Can we find the curve, and can we also determine the signs of that? That's the issue, okay? So, and this as Nash equilibrium simply means this is less equal to, turns out, okay? All right, so first of all, we have to find out such an alpha hat, okay? Well, this alpha hat, because on this line here, this line, okay? Because it's negative, this is 0, so this simply means it's a global, it's a maximum. So it must be a critical point with respect to the second variable, okay? So in other words, we need to find out alpha hat such that partial lambda, partial beta is equal to 0 at those points. And this is called evolution single strategy, okay? Okay, and our first result is the following. So this is what I draw, okay? Okay. So this is a work with Adrian Lan. He's a postdoc at NBI, okay? What we prove is that if m is positive, C2, the ratio between the maximum of m and minimum of m is between 1 and 3 plus 2 squared 2. Then given any gamma positive, if dispersal rate is small, then there exists exactly one evolution single strategy in any finite interval, okay? So in other words, it's pretty simple, maybe, but then it does not tell you the sign of here yet, okay? It only tells you there's a curve intersecting there, okay? Okay. This condition is optimal, turns out. It's a bit interesting that how can these numbers arrive from these models. Maybe this is probably the good part of mathematical modeling, maybe. Okay. All right. So that's the only first part, because we don't know the signs yet, right? Okay. We only know it's a critical point. Okay. So our next result says the following. Our next result says that if U omega is convex, and the gradient of m, the L infinity norm of that is smaller than alpha naught over the diameter of omega. Alpha naught is about 0.814. Okay. Then for small diffusion, this simply means alpha hat is a local ESS. So what we really can only do is we can only do a small neighborhood here. Okay. Okay. So for the small neighborhood, we can determine negative, plus. Okay. That's it. Okay. It's an open problem whether this is a global. Okay. That's tough. Okay. Okay. And this example shows that you can have a very complicated. For example, this one is not evolution stable, and these two are evolution stable. Okay. So let me just quickly mention that, for example, why this domain convex always comes in like such a problem mathematically. Okay, why the diameter of domain comes in? This uses a result of Payne and Helms-Weinberger. Okay, for example, if omega is convex domain in Rn, let mu2 be the second eigenvalue of the Laplacian with normal boundary condition. Well, 0 is the first, right? Then there's optimal estimate low bound for the other eigenvalue that is the square of pi over diameter of omega. Okay. I think I will just stop here. And these are my collaborators. Steve is here, and Chris Kostner. This is my former student. Adrian Rang is a postdoc at the MBI. Shinfuchen at Pittsburgh, Frischoff Lucia is a mass biologist at Ottawa. And Dan Mars is at York. It's my form. Thank you very much. Yeah.